Yes, it is flipped, which is annoying. That's fine.
Doesn't care.
Hello. Hi, everybody.
How are we testing the audio?
Which mic are you using?
Sophia is going to, well, it's just here, but Sophia is going outside,
Yeah.
checking it. If she can hear there. Hi, everybody. Today, we're going to be doing PDR.
Sophia?
You should be.
Doesn't say we're live.
I invited him.
Yeah.
Is it working?
I did see the green. I do see the green thing like go second bar.
Yeah.
So I don't know what that means.
Wait, this is our old one. Oh, it's working. Okay.
So if I'm talking,
We don't have the PowerPoint.
Oh, wait, log in to the. Just go to the drive.
Welcome.
Oh, so it's just like no camera. The camera's just a webcam. Oh my god, it's round.
Wild.
I told you.
And Brian.
Hello.
It's gonna be
Wow. God, I'm just imagining all the NASA external reviewer points.
Yeah. That's when it cut off the audio.
Slideshows. And then probably close.
Thanks.
Yeah, there you go.
Okay.
All right, so.
It's not showing the screen. It's showing it here. I know, but this is the right. It's not sharing the screen. I don't know.
It is.
Like.
Well, but also so is Justin. Not Justin. Yeah, Justin. And Justin is not here.
No, you just said that, and it's not sharing the screen.
Oh.
On the screen, it's like not.
Yeah, this is what it looks like right now. I just joined.
Yeah.
See, there's me.
Oh. There you go.
Okay, sweet.
I think you might be viewing that tab. Nope. No, I'm seeing it.
Great.
Okay.
Perfect.
Can you go up and can you go up and like feel something?
Okay.
Like, I feel something. Like, ask a question.
So I'm confused. Where's the auger? In the dumpster. So
Okay, we're good. We're good. Okay.
Questions you good?
Yeah. We're gonna start in like 2 minutes, so please try to get to your seats and try to sit close. Try not to sit in like dead man's land over there.
We all like each other.
Yeah, sure. You're alumni. Special privileges. What? Stop it. What are you doing? Can you tell the leads there's no more mics? And that is
I feel like we should move this. Can we have the owl like here?
No, let's keep it here.
Keep it here?
Yeah, let's
Okay.
just keep it here. It's okay.
So people gotta be
We can move
loud.
it. We can move it like this.
So it came through well, but they just need to be loud.
Yeah,
like
it came through fine.
You came through like a little vaguely echoey.
Yeah.
Okay, but that the room is a little vaguely echoey, so
That's fine.
maybe not less than you about that.
You were here video projecting.
Yeah.
If someone goes.
Yeah.
That's no one here.
Yeah. Okay. A note for CDR. This is a microphone. You'll notice that I'm very loud. If you want to ask a question, you must too be very loud. So do not try to ask at your normal speaking tone. Try to ask as if you were trying to ask someone all the way in the back of the room, but also like me. Great. Good.
Okay, and then the camera is this little webcam for the people presenting. Awesome. Okay, we'll start. Get the ball rolling. So thank you guys so much for coming to our PDR. This is a really exciting day. We've been preparing for this since SDR, which was successful. So this is the agenda for today. We're going to start with some opening remarks, and then we're going to go into a high-level robot overview from Peter. And then we'll hopefully cover excavation, deposition, and drivetrain, have a lunch break, and then it'll be software and P&H. So yeah. Okay, so for opening remarks, I'm glad that everyone was able to come here today, especially people from outside of Lunabotics, whether you're alumni or you work for the BIDC or just are in industry. We really appreciate it. And we also appreciate the people watching from home. So yeah, feel free to ask questions. Ask questions in the YouTube live stream chat, and we'll be checking those. After each sub-team presentation, we'll be making sure to address those questions. And then we'll also be answering questions in the room as well. As Peter said, try to project. So yeah.
Great, moving on, we're going to quickly go through a high-level robot overview. So the overall system dimensions right now are as such. It's 112.9 centimeters long by 78.2 centimeters wide by 73.7 centimeters tall in its storage configuration. This does fall within the required bounding box for the competition, so our robot is in size. It currently weighs in at 48.53 kilograms in the CAD. This is expected to go up over the following months as we add in fasteners. So if we want to meet our desired weight, our desired mass limits, then we're going to have to find some weight savings. Now the orientation and hoist points, the two arrows indicate the directions of length and width on the robot as required in the NASA rulebook. So length is going to be parallel to the wheels, and width is perpendicular. Also circled in red are the 4 hoist points for the robot. These will be installed with I-bolts, and then we'll have clips inserted into them to lift the robot, as was in last year's design. So here are the 3 system configurations that the robot is going to be running through. There's the starting configuration, which is where excavation is tangent to the bottom of the wheels. This is how the robot will be starting in order to be within the size constraints. To traverse, we're going to raise excavation all the way up on its linear actuators. And that's how we'll be driving around to get ground clearance. And then for mining, we lower the linear actuators all the way so that the bucket elevator digs into the ground. And then one final note on the high-level robot overview is that we have new motors this year, which require special dust protection as the motor controllers integrated are not sealed against dust in the way that we need. So this is going to be accomplished with 2 3D printed motor covers. They're going to have an XTC 3D printing coating applied to them to smooth them out and seal them. There are going to be 6 holes for the required power and data cables. These are going to be, and we're going to have O-rings inserted into grooves such that the cables can seal against the O-rings. And then there is an additional groove in the front for a custom O-ring, which will be sealing against the gearboxes in order to seal off the entire interior of the motor, and then it'll mount at the back with 4 motors, with the 4 motor screws in the same motor screws that hold on the motor controller currently. So with that, we conclude our high-level robot overview, and we can now move on to systems.
Okay, so the first thing we're going to talk about for systems is the CONOPS, the concept of operations. This is an overview of how the robot will accomplish this task. It consists of the objectives for the robot, the requirements the robot must meet while achieving those objectives, and any environmental factors that will impact the objectives and the requirements. These all inform the operations process, which will be detailed on the next few slides. So first, our objectives. A robot is successful if it can efficiently and reliably traverse without damaging itself, collect regolith, construct a berm in the respected areas, and operate safely without posing a hazard to any individuals. And these are further defined and made more specific in the stakeholder requirements. So this is our concept of operations, our high-level operations process. This will be included in the systems paper once it reaches its final version. So this is preliminary now and will be more refined when software does more work, but this shows the startup phase of the robot. Initially, it'll do its initial ascent, it'll map, it'll select its excavation location, traverse there, it'll mine, and then select its deposition location, traverse there, and then it'll go back to where it started. So some current risks that are high priority for us right now are safety. we ensure that our robot has a safe mode that is detailed on the operations process that you saw on the previous slide, and further requirements for that are in the robot system requirements. We also worry about part failures. Components identified to have a high risk of failure must have at least one spare and must be procurable overnight or easily manufacturable in our pit for competition. Here are our TPMs, our technical performance measures. These are updated based on the CAD model right now. So as you can see, some of these Peter already went over, but we have an initial mass estimate. We have estimates for power, bandwidth usage, the dimensions of the system, things like that. These will all be further updated throughout the season at later reviews. So now we're going to get on to estimating our scoring for this year. So here are very preliminary estimates of our cycle time and speeds. So we estimate one total cycle will take about 4 minutes, and you can see the components of that there. These are parts of our subsystem TPMs. This is a pretty conservative estimate based on our final TPMs from last year. It was something like 3.6. So this seems pretty reasonable. And then you can see how that translates into how many full cycles we can do in a cycle. It just means, going to the excavation location, getting regolith, bringing it back to the deposition location. So you can see how many cycles that translates to for both the 30-minute KSC run or the 50-minute UCF run. And if we assume about 10 liters per cycle, which would be about half the total volume of our regolith storage, you can see how much volume of regolith would be deposited. So we can use those estimates to estimate our scoring. So if you look at the pre-operation scoring, so we are first get a scoring penalty based on how many situational awareness cameras we use. So if we don't use any of those, we can get a full 120 points. If we use one, we'll get 60. And if we use two, we're not going to get any of those. And we just get 23 points for passing the inspection. For berm construction, very similar to last year, there's a target area and you're scored on how much volume you can get there. Basically, you get scores for one is normalized by the robot's mass, one is normalized by the energy consumption, and those both factor into your score. So you can see some estimates here for both the KSC and the UCF. So we have the normalized for robot mass and then normalized for energy. And you can see here in the expected score column, you can see the estimates based on those cycle time estimates that we gave earlier for what a berm construction score that we get would look like. Another important category of the scoring is the dust tolerant and dust-free points that we get. So these are all judged categories of points. We get points for dust tolerance and dust-free operation. So we can expect to get points for protecting our drivetrain components and for some custom dust sealing features. And if we include further things like active dust mitigation, we can get more of these points. Autonomy is the next big category. This chart here that NASA provided summarizes the types of autonomy combinations that we can get based on if we can do a full cycle or part of a cycle or none at all. So we can, if we're consistent with what we did last year, we can expect to get an excavation and dump autonomy, which would get us 150 construction points. So if we add up those rough estimates, this would be our total score. It's not comparable to last year because all the weights are different, but it would be about 613. And you can see how that breaks down into the pre-operation, berm construction, dust tolerance, and autonomy. And there's just the percentages there, so you can see how much each of those contribute. Also, there is a calculator in the drive as listed there if you want to play around to see how getting different types of points would impact our overall score. So for UCF, the Bourbon construction scores from each one will be added together for the final score, so that's cumulative, and then the top 10 move on to KSC. And there, the scoring is based on the construction points ranking. First, second, third, you can see the table there, how many points they get. And then if you're not on those, you get 1 point for every 0.2 cubic meters up to 10 total points. And lastly, for the Artemis Award, which is one of the awards that we could get, the points are allocated for some of the other deliverables we have too. Like you get 15 points from the STEM engagement report score, and only 25 of those points come directly from the robot construction score. So next we have excavation.
Okay, to start off excavation, I'm just gonna go over a high-level system overview of our bucket elevator system. So, surprise, surprise, this year we're going with a bucket elevator. Pretty much how it works is we have a timing belt sitting on 2 metal 3 printed drums on the top and the bottom of the system. And these drums are pulled apart via tensioner and driven by a motor sitting in the top assembly. These motors drive the belt, which have buckets fixed to them. And we use linear actuators to plunge the system into the ground while driving the motors to excavate regolith out of the ground, up and over the system, and into the deposition system. Last year, we went with a trencher system, which was a little bit different. Pretty much how it was last year, we were rotating the opposite direction and pushing material up a scrape plate in the back. Last year, we had a lot of issues with jamming, especially, and stalling of our motors, mainly because the regolith or the gravel was getting stuck between the scrape plate and like the belt, and it was causing a lot of issues with our motor stalling. So that's sort of why we are moving away from the trencher this year and returning back to the bucket elevator. One thing we're really focusing on this year is reliability. In the past, we've had various reliability issues with our mining systems, whether it be gravel getting stuck in the drums or motor stalling. So that's why, and we seem to have fixed most of these issues, especially with the gravel getting stuck in the drums. We now have covers over the drums, and we had this last year as well, and that seemed to solve the issue completely. And then the other issue is mainly with stalling. And we think that issue should be solved this year, mainly by abandoning the scrape plate design, but also we have new motors this year. This year we are going with 200-watt motors with a 50-to-1 reduction. This allows us to spin the drums at 60 RPM with a 32 Newton meter rated torque and 96 Newton meter peak torque. That's a lot of torque. That's a lot more than last year. So I don't think stalling will be an issue this year. Also, these motors are a lot better. So using the new motors, and we'll be operating at like a faster speed this year. The drums will be spinning at 60 RPMs, which allows us to have an estimated volume throughput of about 11.5 liters per minute. This is a pretty conservative estimate based on our calculations. And we expect to fill deposition in about 1 to 2 minutes, which is within our design requirements. Our other design requirements is our mass. Right now we're sitting at a mass of about 16.5 kilos without fasteners. This seems a bit heavier than in the past, but it is mostly due to the new motors, which are a bit heavier than before. And our last system requirement is the bounding box height. So we're sitting at 0.737 meters, which is pretty close to the 0.75 meter maximum, but we had to make some adjustments to make sure we met that, but we're well within the 0.75 meters, and that 0.737 is a worst case scenario. So now I'd like to speak a little bit about Our structural design, we're going with a 3-rod structural design. As you can see in the bottom photo, we have 3 rods spaced apart in a triangular pattern. This has worked out really well in the past, especially our system hasn't had much rigidity issues with the rods, mainly because they're made out of steel. So no deflection of the rods for that. One thing we are changing this year is we decided to move the rod or spread the rods further apart, mainly because last year we were experiencing some bending in the top plate. So we're moving those out this year. That should fix the issue because most of the load on that top plate is near the outer edges, and by placing the rods closer to the load, it should reduce the stress and bending on that plate.
So whenever we wanted to move the 3 rods apart, we incorporated all of our parts we used in previous years to support the 3 rods. However, when we did so, these supports that guided the rods were a little too big and had too large of a radius between the screws that went into the plate. And because of that, we needed to redesign those. So we went with these custom supports that are in this rectangular shape that bring the radius of the screws that go into the plate to be closer and have a smaller radius, and they utilize a set screw to make sure it's all held together. And then we also this year changed this, which is the pancake tensioner. The pancake tensioner this year is fixed on the bottom. It's a screw that's fixed on the bottom with 2 guides that fix the rotation of the rectangular screw head. And the reason why this is different than the previous years, because previous years we have to get a grip on the screw and a nut to tension a pancake tensioner. However, this year, fixing the rotation of the screws and having 2 will not only increase the amount of force we can have on them, but it also makes it so that instead of having to finagle our way into the robot and get a grasp of both the screw and the nut, now we can just screw the nut from the top, which should make the entire process easier.
All right. So this year we are moving back to a bucket elevator, obviously. So for that we need buckets. Our plan is to weld 2 different pieces of sheet metal or L channel together. We have an L channel, which will be 1 inch by 1 inch and 1/8 of an inch thick. And we'll have another piece of bended sheet metal that'll have 2 bends on the sides and is also 1/8 of an inch thick. These will be welded together at the bottom of the L channel, as you can see at the bottom of both pieces, and then at the back side. The entire bucket will be about 1.2 inches by 1.1 inches by 4.5 inches. And it'll be fastened to the belt with bolts.
So new this year, we have a dust cover on the excavation system. Now this is to prevent dust from being spewed about and all of that. And with the bucket elevator this year, the fact that, as Julian mentioned, we're going to be running it much faster than we have in the past, it will require more protection to prevent dust from being spewed all over the place. In addition, it also prevents debris from being shot out of the bag, so just also helpful with the safety thing and for preventing things from getting damaged and stuff. Additionally, we have 2 parts of it. We have the frame, which will be what connects the dust cover to the actual excavation system itself, and then the actual cover will be made of a nylon fabric. And we decided on using coated nylon because we went through a bunch of different fabrics, and we were like, okay, which one has the strength that we need and is resistant to abrasion and tearing and all of this. And we set it on coated nylon because it just was the best of the options that we looked at. So with that, with the plate itself being, the frame being connected to the excavation system, it will be connected at 3 points on the top, middle, and bottom for stability. Each one's going to be fastened with an L channel and then screwed in. And then for the actual cover itself, we're going to be putting some holes into the fabric and then creating eyelets, which will then go on top of holes on the frame, which would then be fastened using rivets.
All right, so in terms of our actuators, we are using linear actuators. We have 2 of them in our system, and they're going to be the same ones that we used in the past years. Each of them have 8-inch strokes, and they're both rated for 50 pounds of force, which means in total we have 100 pounds of force for our system. The system will be actuated into the ground, so kind of expected out of excavation. And the major changes that we're doing this year in terms of our actuators is how we're mounting them. So in the past years, we mounted our actuators by seating it through the support plate, and it was held in place by a pin, which proved very difficult to reach and actually secure. So this year, instead of that, we're going to be securing it on top of the support plate, and it's going to be fastened between a L channel and then an extension of our side support plate on the excavation. And that pretty much wraps it up. I'm going to pass it along.
Okay, so now we're moving on to our DFMEAs. So we evaluated various failure modes of our system, and I'm just going to go over a couple of them that I think are pretty important. So first, I'd like to go over the buckets and what may happen with the buckets, especially with the welds we're going this year. We haven't proven the welds yet, and we don't know how strong they are exactly. They should be strong, but it all depends on our welding skills. So we're a bit worried about the buckets possibly deforming or the leading edge maybe falling off. This would result in a degradation of system performance. It's not completely catastrophic because it's very unlikely that every single bucket will fail, but it's possible that one may. I would say it's likely, I would say it's improbable, likely, somewhere in between. It all depends on our welding skills. And we hope to mitigate this by trying to do a good job with the welds and also make extra buckets just in case we have issues with this. Another issue we've had in the past is with the motors, mainly with stalling. This was a pretty common occurrence beforehand. We hope it's not an issue this year, so the likelihood will hopefully be less. It may cause a reduction in performance, mainly because in the past, whenever the motor stalls, we have to stop mining for a bit. So it may affect our total volume throughput, but it wouldn't be completely catastrophic since we just slow down mining, reverse, and restart running the motors again. And also, there are some fail safes in place with the motors. In the past, we've had sensors on them to prevent actually damaging the motors. So next up, we'll talk a little bit about how the actuators may fail. In terms of how an actuator might fail is you either have like a hardware failure with the actuator itself. I'm not too worried about that since they've been proven pretty reliable in the past. Another way they might fail is due to some deflection in our struck rods, since our linear actuators are pushing our system up and down on that axis. So if we have any deflection of those struck rods, it might cause binding on the linear actuators, which may cause may exceed the rated load of these actuators and cause stalling. I don't think it's super likely, mainly because the tripod or the triple rod design has been proven and has worked in the past, and we haven't had any issues with linear actuators binding. And then finally, there's some other failures, mainly with some of our plates. We are worried about buckling of our top side plates, mainly because this year we are exploring weight saving measures in those areas. Last year we had our top side plates were about a 1/4 inch thick last year, and this year we're trying to reduce that down to 1/8. We've done some basic analysis. We've done some buckling analysis on it, and for now it seems fine, but it's something we might have to worry about, especially since in one of our side plates there's a large cutout, so it may be prone to buckling. And if our system buckles, that'd be very catastrophic because the belt would lose tension and possibly fall off and cause either harm someone or completely ruin our run in competition. And we can mitigate this by doing a lot of analysis and then making sure we validate that analysis in our testing. It's sort of the same thing with our top and bottom support plates. In the past, they have bent, and we're hoping to fix that this year, but it's not completely catastrophic if our top and bottom structure plates bend a little bit. And we actually ran it last year with some bending and it was okay. So I'm not too worried about that, but we have done things this year to try and mitigate that. And again, we'll do a lot of analysis on that to make sure it doesn't happen again. And to wrap up with our priorities moving forward, first, we will implement the feedback from this design review. That'll be a main focus between now and the next one. And then we'll also be working on dust covers since we don't have those done yet. And also inserting fasteners, exploring more weight-saving options. And then also we plan on we're gonna start running our mining force experiments and then start experiment and training with welding the buckets. So that pretty much wraps up excavation. So now I'm gonna open up the floor to any questions.
We have one question from YouTube right now, and they're asking if we have any plans to do any destructive testing with extra buckets, get an idea of when the buckets will likely fail.
So the question was, will we do destructive testing on the buckets to figure out when they fail? It is something we can explore. We haven't done that much in the past, but we do have a lot of manpower this year to try and work on that. And we'll also, maybe it's something we can do alongside our mining force experiments. So I'd definitely like to explore that this year.
So for your buckets, first of all, what alloy are you thinking for your 8-inch bends?
So the question is, what alloy are we thinking for 8-inch bends? 8-inch, sorry. So the buckets will be made out of aluminum 661. I've gone and asked the people at Bechtol's Hot Works to see if it was actually possible. And they said that aluminum welding is actually possible on 8-inch. And they said our design, they gave us some feedback and we implemented that into our design. And they said it's possible and shouldn't be too hard. So I'm not too worried.
We actually have someone from Hot Works, yeah.
Yeah.
So the 6061 is gonna wrinkle when you have that.
Yeah.
You can weld it, but I'd be careful about bending it like that.
Okay. Do you have any recommendations for that?
3003.
Or 60.
Any of the other options, or you just weld that side piece on instead of bending that side piece on.
Okay.
6060 will weld either, but it won't like that.
But 3003 wouldn't have.
Yeah.
I was gonna say, we thought about using, especially talked about this, using 16-inch aluminum and basically cutting out the buckets and just bending it that way. You can do some destructive testing and see how well it stands out.
Yeah, so the suggestion was looking at 16th-inch aluminum and laser cutting out the buckets. So that's something that we should definitely explore, especially because it would also save on mass. So it sort of killed two birds with one stone. And if we do some destructive testing and it proves to work, that's definitely something we should try and implement. So good question.
So on your new actuators, you mentioned that you plan on using the same actuators as this year. Our current actuators this year are 150-pound actuators, not 50-pound actuators. Do you plan on continuing? Do you plan on changing it out of 150-pound actuators, or do you plan on continuing with 150?
Okay, so the question is, so apparently the linear actuators from last year are rated for 150 pounds each, and whether we are going to be using those. So the answer is yes. That was just sort of overlooked, I guess. For some reason, I thought we were using the 50-pound ones. Okay.
Yeah, so since the welding of the buckets is relatively new, if the bucket, so doing the destructive testing is probably nice, but maybe with also how you're attaching it. If the bucket fails at any point on the belts, do you have analysis of if the system can continue running depending on how that bucket fails? As there's many buckets, so if one of them fails, you have a way of making sure that the rest of the system can still function.
The rest of the system, so the question is whether if a bucket fails, can the rest of the system still operate properly? So I would say it depends where it fails. I would say the only way it would be completely catastrophic is if a bucket fails and then causes a jam in the system. If the bucket just falls off into the regolith, the system can operate perfectly fine. But if that bucket fails and then causes a jam and stalls our motors, that may be a really catastrophic issue.
So that goes to the fabric part or the dust covers, right? With the cover there now, there may be a chance that it might get stuck in there somehow. Is there a way to, well, first, how are you tensioning that fabric to make sure it doesn't interfere with the buckets when it's running, with the vibrational forces and making it flex? And then if a bucket fails inside that area, is it still safe to just throw it out the back?
Okay, so the question is regarding buckets failing and our excavation cover and how we plan on tensioning the fabric. So I'm going to start off with how we plan on tensioning the fabric. We plan on tensioning it with our fixtures. It doesn't have to be super taut, but it definitely can't be sagging too much. We do have over 1/2 inch of clearance between our buckets and the fabric, so that should give us some leeway there. In terms of a bucket failing inside of the excavation cover, I would say it is a bit of a concern, and we'll definitely have to explore that a bit. Because there are like kind of two ways it could go. Like a part could fall off and it could tear our cover, or the bucket can fall off and it can go out the back, or it can just be driven up in another bucket and just pushed out the back, and that wouldn't cause any issues. But sort of the same answer to the last question about buckets failing. As long as it doesn't cause a jam in the system, it wouldn't be completely catastrophic, because even if we have a tear in our cover, that wouldn't be an end of run kind of event.
About the excavation cover, you mentioned it was attached with rivets. Is that the excavation cover to the robot is attached with rivets, or the cover to the excavation, or the metal to the excavation?
Okay, so the question is whether the how the excavation cover is fastened. It's regarding if the cover is attached with rivets or fastener, and if the cover is attached to the robot with rivets or fastener. So
yeah, sorry. So the cover itself, like the actual fabric, is going to be connected with rivets. I'm not 100% sure about how it's supposed to be connected to the actual with fasteners. So it's just fasteners for the actual excavation system itself. Yes.
So if the cover was to rip, the rivet's like in there. Like you can't you're gonna have to put another rivet in if the nylon rips.
Yes. Yeah.
Okay. Okay. We have another question about the motivation behind the width and depth of the buckets. They seem pretty small.
So the question is, what is our motivation with the width and the depth of our buckets? So the main motivation is we're pretty limited on our height this year. We're pretty close to that 0.75, and any increase in the depth of the bucket has a twofold increase on our total system height. So we're sort of limited there, especially since we're not changing the belt this year. So because last year we were very close to that height limit, so we don't have much to play around there. That's something we can mess with in the future, but I don't see it changing that drastically, mainly because our height limit.
Yeah, so going back to the rivets with the dust cover, dust cover. Have you thought about how you clean out the system, or if something stalls in there, you need to get in there? I feel like it would be difficult to access this that is permanently attached with rivets.
Okay, so the question is access inside of the excavation dust cover, just in case something fails, or to clean it out. So since the excavation cover is traditionally fastened to the excavation system itself. We're only using rivets for like for the fabric part of it. We should be able to easily remove the excavation cover by undoing those normal fasteners.
So a suggestion for, instead of using rivets to attach to the dust covered excavation, you could instead use fabric snap fasteners. Then you could just quickly take off just the fabric. And then that way, in the case of a bucket gets caught, it might just take the fabric off instead of it. So.
Okay. So someone made a suggestion about using snap fasteners to prevent, help prevent the excavation cover from ripping. In the case that there is something that might cause a rip, that would cause the excavation cover to just fall off instead of ripping.
After this question, we might have to move on to the
Okay.
next. Yeah.
Okay, can you go back to the mounting of your actuators?
Yeah.
So I think that this was a reaction because when we did this in previous years, we managed to bend the bolts that were holding it on. I think that's why it was mounted the other way. There was more of a problem on top of the actuator, but I think it did happen slightly on the bottom. So as a comment, if you can use like a partially threaded piece here, I think it would do a lot better and give you freer rotation.
Okay, so there's a suggestion made regarding the linear actuator mounts. In the past, it seems like we have bent bolts trying to mount actuators like this. So it's suggested that we do a partially threaded sort of mount to give us more rigidity and freedom there. All right, so that wraps up deposition or excavation, and we'll be moving on to deposition.
Hello. So for this year, we decided to completely redesign the deposition system from scratch and replace the over deposition system with a conveyor belt. Dimensions of conveyor are going to be 60.56 inches by 10 inches. The usable surface which regolith will be deposited on will be 24 inches by 10 inches. It will use brushless 200 watts motor, take around 8 seconds to deposit. The current weight of the system is 9.29 kilograms, and it can hold up to 20 liters of regolith.
So the structure of the deposition system, we have a couple different walls. The darker gray walls are 1/4 inch aluminum, which provide the structure. Everything is attached to them. The pulleys are attached to them, and the other walls are as well. The motor is in the bottom of this picture here. We're going to have 2 pulleys and then 2 idle rollers in the middle there. And then one is going to be an active pulley with a motor. There's going to be 3 additional 1/8 inch polycarbonate sidewalls, just because those are just meant to keep the dust in, not actually bear any weight, so they don't have to be super rigid. We're also going to have 2 3D printed triangular ramps. Those are going to be, we're going to show those in the next slide, but those are going to keep the dust from falling through the outer edge of the conveyor and hopefully funnel them into the center of the conveyor so it doesn't get lost.
So the triangular side ramps are basically 3D printed pieces of plastic which will be covering just above the surface of the conveyor belt. This way it will hopefully prevent the regolith from getting lost through the gaps on the sides of the conveyor belt and prevent any friction of conveyor belt with the sidewalls. They're 3D printed, and in case they would not work, they can be adapted to be maybe holders for brushes, or maybe be adapted to be some kind of other design, which can be still attached to the same mounting holes to the main aluminum sidewall. So it's pretty customizable, and we can change it anytime we want.
So next I'm going to talk about mounting and tensioning. We are mounting to the drivetrain frame with 4 L brackets. These are not going to be uniform on our system. They're going to be spaced in a way that doesn't interfere with any other things going on in the drivetrain frame. The belt tensioner is going to be on the deposition side, or the back side of the robots. It's going to have this solid brick that you see in the right picture there. There's going to be a screw going through it, and turning of the screw pushes out the shaft there. So it'll slide in that slot and then tension the belt.
So for the motor, we will have final RPM of 15. The original motor RPM is going to be 3,000, but we will probably run it at a lower voltage or lower current output. It is connected to a 50-to-1 gearbox and then 1-to-1 sprocket chain link. It can get up to 128 Newton meters rated torque, and it's connected to the drivetrain pulley, to the driving pulley of the conveyor belt by a chain.
So here's our DFMEA. We looked at all of our components from the conveyor belt, pulley, belt tensioner, and frame. For most of these all these issues should be mitigated, mostly if we do our due diligence and research modeling and during construction. Our main concerns are with these two for the conveyor belt in terms of the belt being overstretched, which is kind of hard to determine unless we analyze the loss of efficiency, and also with the dust getting between the pulley and belt. With the first one here, we just need to look into what belt we purchased and have the details of how much elongation is necessary and do our calculations for that. And for dust mitigation, of course, that's great for the whole robot. We just need to develop a better system for dust-proofing. Yeah.
So priorities moving forward is to optimize the triangular side ramp for 3D printing by breaking it into multiple parts which can be fit on the 3D printer bed. Another priority is going to be dust mitigation and dust protection. We will design dust covers and for pretty much everything and analyze what else can be done to prevent regolith from damaging the system. We will also implement weight reduction measures, research possibility of active dust mitigation, start preparing for manufacturing by inserting fasteners, choosing our parts, making plans and optimizing for manufacturing. And we will also research alternatives and look into custom manufacturing for some of the parts, mainly the main pulley for the driving pulley, because it's pretty expensive as we are configured it right now. So we might make it custom or try to see if there's any other suppliers with a better pricing. Does anybody have any questions? Peter?
A couple questions. First, the triangular side ramps, how long are they?
They go through the entire length of the robot, and they're currently 1 inch long. We will probably might make them even longer.
No, in terms of length, they're 24 inches long?
Yeah, 24.
24 inches long? Okay. Do you plan to split that up into multiple pieces that we connected together?
Yeah, basically, we'll probably split them into a few pieces, which will be 3D printed separately, and then kind of connected together.
Okay, good. Second question. Right now, you said that you want to run at about 15 RPM, right? So 3,000 3000 RPM gearbox motor, 51 gearbox. The rated speed is 60, so you're running the motor about 25% speed. Would you consider making the gear ratio slightly higher in order for we can run the motor at a slightly more perhaps efficient speed?
Yeah, we will also probably might use a 100 to 1 gearbox instead with the similar dimensions.
Okay, final question. Is there any static components which connect the two sides together?
No, both of the main sidewalls are connected to the drivetrain, and then they support the rollers and the pulleys in between them.
Okay.
There is a polycarbonate sidewall, but we're assuming it's not going to. We're not designing it to carry any weight or any loads.
Okay. I think that you might want to add such a support or connecting in between the two plates such that the space between them can be kept more consistent. In terms of, only a couple of assemblies, only a couple of screw joints as opposed to, relying on drivetrains, precision. Not the drivetrain in precise.
Okay, Sophia?
I have a couple questions and then one from YouTube, but for the polycarb sidewalls, I saw that there's L channels or securing them or L brackets I meant. Will it fracture the polycarb? I've never drilled into polycarb before. Can it be faster than polycarb?
We don't know that. If it fractures polycarbonate, we might replace it with different plastics.
Okay, and then my next question was, what's the clearance from the motor to the ground in respect to drivetrain, because it's mounted under the conveyor? What are the odds of a rock? We drive over a rock and it hits the motor.
It's about the same. I'm not sure, but it should be. It's around at the same distance from the ground as the drivetrain motors.
Okay.
So we're assuming it's going to be fine.
Okay, and then from YouTube, someone asked on the first overview slide, the gears connecting the motor and the conveyor appear to be very thin. Could this represent a problem?
I can actually answer that. The slide is slightly out of date. Those aren't gears, they're actually sprockets. I don't know why the slides are out of date, but in the current design, the sprockets are actually much smaller and one-to-one.
Yeah, the slides probably haven't updated since we made some design changes quite recently.
Okay.
Hans?
What type of chain are you using?
Question, what type of chain are we using?
Number 25.
Number 25. Alex?
So your openings conveyor belt system. What belt are you using?
We're going to use a brown neoprene conveyor belt.
More questions. You mentioned that you were using ABS for your triangular ramps. Why? And shouldn't you be using PLA instead?
Apparently, ABS is more abrasion resistant compared to PLA. So I would prefer to use ABS just because it's going to be touching regolith quite a lot.
Can you use something like PEG instead? It's going to make your printing life much, much easier.
Yeah, we can potentially look into other plastics as well.
I've got a concern about the ABS as well. When you print such long objects with ABS that warps, you're going to lose all sort of sealing. So your dust protection will get affected.
It's mounted to the aluminum sidewalls at multiple places. So this should help with the bending. The question was whether ABS triangular ramps can bend, because
He's saying when it prints.
when it prints.
Manufactured, but it's not going to seal to that plate correctly. So now you got gaps in it. Because ABS is just filler, right? So
Yeah.
You're going to have cracks and wrinkles in it. So that's where you're going to get dust coming out the back end. When it comes out the back end, it's going to land right on your roller. If you have any type of lubricant on your roller, it's not just
The rollers have built-in bearings inside of them, and they should be sealed. So this should not present any significant challenges.
Going back to triangle, how are you actually mounting them to the walls?
I'm actually gonna go back a few slides just. To the walls. So it might be hard to see, but there's 4 holes on the aluminum side plate. So we will just we would put some kind of like, actually I forgot the name of the part, but we're gonna have like something metal inside of the inside of the ABS sidewalls, and then we're gonna just put like a screw through those 4 holes to hold it in place.
They're like heat inserts, yeah.
Yeah, heat inserts. Hans?
You go back to the custom pump tensioner.
This one?
Yes. So is that bolt, is that just pushing on the axle for the pulley, or is that actually threaded?
So it's not going to be threaded into the shaft. The shaft is just going to have a flat side where the bolt will push against, and the block is threaded. Max?
Yeah, 2 things. So first, with that ramp at the bottom of the triangle and the belt, what is the distance that you plan to have that? Is it going to sit right on top of it, or how much clearance are you going to design?
We're currently maybe 1/8 of an inch, potentially maybe make it slightly lower or higher, depending how the testing goes. Since it's 3D printable, it's very easy to adjust it by just like shifting the location of the heat insert.
Okay. Yeah, because keep in mind that if it's too close, you'll have the belt rubbing up against it. And so if it's intended for that, if you want some sort of like seal, you might need to do something to make sure that it doesn't have excessive wear on the bottom. If the distance is too wide, then you won't have the benefit of the sealing. So maybe that might not be the solution you need for that. But okay, that's good to know. And then the second thing is, how do you plan on assembling the system together with the rods in the center? What's that looking like? Do you have an idea?
The question was how we are going to assemble the system with all the rollers and pulleys in the middle. So the idle pulley and the driving pulley are using shaft, which will be inserted through the holes on in the aluminum sidewalls. And for the rollers, they're spring-in installation method, so you can just push the sides of the shafts into them and just like slide it in. And conveyor belt will be placed inside of the system before the installation.
You're almost like installing it like side up, like you would do part of the deposition box and then put in the rods and then put in the pulley and then put in the other side.
Yeah.
Okay.
Isaac?
With the mounting, do you guys have place for load cells anywhere?
Not the right question is, can we place, do we have a place to put load cells anywhere? Currently, no. One of the L brackets is custom, it actually has similar dimensions to the load cells, so theoretically we can try to do that. I'm not sure how accurate this will be, because it's one of the, but yeah, we can look into that. But you would definitely have to do a lot of calibration, because it has, the weight is not going to be distributed equally.
So one concern with the bell, I don't know if we've had this issue before while the team decided, but a concern with the regolith getting stuck to the bell, that we need to treat it or something, or just come off.
The question is about regolith sticking to the belt. So currently we're using a low friction belt, so hopefully it will help with that. Low friction top belt. Also, we might look into installing scrubber or brush at the very end, at the back of the system, which will clean it while it goes back.
So you mentioned you have polycarbonate sidewalls, and you said those are basically only there to keep the dust in. Can you go thinner than 8" for weight limiting reasons? Can you go with like 16 to 32nd from the extreme playground or something?
Is polycarb that heavy? It's like plastic, right?
I'm not sure how much we're saving. I'm pretty sure it was pretty light. But yeah, we can probably look into that as well.
I think it's just like all the bearings and the rollers, like which no way.
Yeah, majority of the weight is the aluminum sidewalls, the rollers, and the pulleys.
On the point of aluminum sidewalls, have you run FEA? Do those need to be quarter inch thick, or can you bump that down to something better?
Currently, we have like a lot of like issues running FEA due to like some of the components parts not meshing properly. So we haven't run a proper FEA yet, but preliminary FEA shows that it should be fine. So we might look into decreasing the thickness or maybe doing some kind of weight-saving cutouts later. And this is actually going to be one of our top priorities moving forward. Andrew?
So along the same lines of the side plates being quarter inch, have you thought about keeping and her suggestion is to keep the bottom half of it where everything, the motors and everything attached to the frame, keeping that quarter inch and then taking it into a CNC and machining the top half down to an 1/8 inch or so that way it's less clear.
Yeah, this should be fine, especially since the top plate is mainly to top part of the top part of the sidewall is just mainly to support the polycarbonate sidewalls and the 3D printed ramp, which should not have any loads on them.
I have a question about the actual, I think that one right there. Is there anything holding it from moving, I guess, actually setting out? Because there's a lot of questions on exactly how it's going to work. But just saying, have anything like this?
We'll probably maybe put some kind of like something to constrain it relative to the idle pulley.
Also, the picture's a little, the actual pulley that's on it.
Yeah, the actual pulley is made invisible in that picture. So I'm gonna see if there's any other picture. I don't think there's better pictures than this. But in the back, there's like an idle pulley with built-in rollers. So we will probably build something around there. Any more questions?
What's the red size on that tensioner screw?
Right now it's 1024, but we will probably might change it later. Any other questions? Peter?
Yeah, can you go to the back view of the system?
Like
the back view, like the view, yes.
Yeah.
So it looks like, so right now you have I believe it looks like a half an inch gap between the belt and the sides of the wall. Is there any particular reason for that, and could you make it smaller?
Main reason is the pulley, the idle rollers are designed to be wider than the belt, and we're both rollers designed for 11-inch gap, while we have 10-inch belt, because the other size is going to be too small. Another reason is to prevent the friction of the belt against the sidewalls, and we're going to use the triangular side ramps to keep the regularly thin to compensate for those gaps. Alex?
You have a way, so if there's a gap on either side of the belt, do you have a way to prevent the belt from moving left and right?
We will connect something to one of the pulleys to keep it in place. Are there any other questions?
Right over there.
Oh.
I just want to clarify something. So this year, the decision system isn't like a STEM system. It's like the one connected drivetrain and then separate. The bill is separate. It's like it's not its own assembly this year. Am I getting that right?
Yeah, it is sub-assembly, but this year's conveyor belt is a sub-assembly, but it will be reliant on drivetrain for structural stability. We will add something to keep connecting the sidewalls together later, but it's gonna mainly rely on drivetrain a lot for the actual mounting.
And is there only one mounting point on each side?
Okay, there's 4 L brackets. You can only see one on them on this picture, unfortunately. There's 2 on the other side, on the back, and then there's another one on the other side of the extension in the bottom corner.
Yeah, I know for previous years, drivetrain has a tendency to fluctuate the channels and stuff, so anyway, keeping the walls in place, if not relying on that.
So currently we mounted the position to the drivetrain for mainly weight saving measures. But if like fluctuation would be an issue, we would reinforce it and try to make it more independent sub-assembly. Hopefully it won't happen. Yeah.
Awesome.
Okay, I'm gonna hand it off to. Are we done with questions?
All right, we're gonna start with drivetrain, which is what our CAD looks like right now. This is our current top level assembly, just for a sense of scale. Okay, a quick system overview. We ended up going with almost everything we had said we were gonna go with at SDR. So just a recap of that, we're gonna continue with the trend of a linear gearbox arrangement. So no 90-degree gearboxes. We're keeping our chain drive system. We had considered pulleys, but in the end, we're going with a chain drive. We are improving our chain tensioner though. That was a concern from last year. So we have a solution for that. We do have a new wheel design. So we're calling it the box grouser design. And we're going with 1/8-inch square box tube with a weight savings pattern that is not in the CAD yet. We've been doing FEA analysis on several designs to figure out which one will work best for us. And then system sizes and masses. We were allotted 20 kilograms. Our system size currently is those numbers up there. That is within the system bounds and is really close on the width, but we believe that there's enough wiggle room there that we'll be fine. And as mass comparison for last year, we're currently sitting at lighter than where we were last year, but that is without fasteners, but it's also without weight saving soles. So we expect it to be maybe slightly heavier than what is on there right now. Right.
All right, so updated frame from last year. The current estimated mass is going to be about 3.89 kilograms. Overall dimensions is it's going to be 32 inches long by 16 inches wide. That is about a 4-inch decrease in width from last year. Box tubes are going to be 2-inch by 2-inch by 1/8-inch thick. During CDR, we had kind of been debating about different wall thicknesses for the box tubes from 16th inch, 3/32, and 1/8 inch. We have eliminated 16th inch as an option due to various strength and manufacturing concerns. We are still kind of looking into 3/32 inch pending on findings of FEA and so on. So as of right now, we are moving forward with 1/8 inch wall thickness for the box tubes. In terms of joints, at the back of the frame, it's going to be using 4-inch by 2-inch by 1/8-inch thick gusset plates on the top and bottom of the frame. And then at the front support tube, it's going to be 2 by 2-inch L channels that are an 1/8-inch thick. As Hans mentioned, with weight saving patterns, we're currently running FAA on various designs that we have for those, determining which one is going to perform the best, and then also trying to figure out a final design for those patterns.
Thank you.
All right, so this next slide is about our clearance for the drivetrain. With the wheels increasing in size going this year, our clearance measures had to be redone. The numbers calculated here, the numbers calculated for this can be seen on the slide, with both images depicting roughly where the measurements took place. as a comparison from last year, both of these numbers about doubled. So one of the problems we not super ran into last year, but was a slight problem, is just our general clearance. Like we could kind of drive over things, but there were once or twice where we just beached ourselves on a rock from just getting stuck on our skid plates. So with this is purely drivetrain measures. Excavation clearance wasn't fully taken into account here, but with this, we should have a lot more freedom on the software side to just kind of drive over things, hopefully.
Thank you, Belle.
So for the gearboxes, the rear gearbox will be the one with the motor. It'll be a motor and a 50-to-1 gearbox assembly, which gives 32 Newton meter rated torque with 92 Newton meter peak torque. The gearbox assemblies will be using 35 chain with rivet nut mounting to attach it to the frame and a shaft collar to hold the wheel in place. The front gearbox will also be using the same chain, obviously, with rivet nut mounting as well for the frame and the shaft collar to hold the wheel in place.
And then next up is our current chain changer design. We did a bit of remodeling because last year's needed some updates. So currently our design is just to have a slot through the frame with a just large sprocket that runs all tension of the chain. Currently pictured is what we're looking at. We are currently also looking into using just a larger sprocket to get better tensioning.
Okay, moving on to wheels. This was something we looked into a lot this year. From SDR to now, what we ended up doing is after the discussion from SDR, we did, for those who remember, we had 3 designs originally, and we did decide to let go of our dimpled design, and we moved on with the box grouser and a mesh wheel design. And those groups will talk about their prototyping and results now.
Yeah, for the mesh wheel design, we 3D printed those rims on the center support, and we attached them using wooden dowels that went through holes in both the rims and the wooden support in the middle. And then we attached some stainless steel chicken wire to it to kind of imitate our idea of making a flexible wheel. And then we attached it all using zip ties in the end, because just to make sure that it didn't come out. And then with that, we tested it for like flexibility and sinkage and traction, which.
Right, so for testing wise, we wanted to test sinkage and later traction. So first we tested sinkage by first adding 5.5 pounds on top of it, and then followed up by 11 pounds to simulate the weight of the entire robot on top of it. And there wasn't much actual data collected quantitative-wise, but qualitative. We noticed that the chicken wire was holding up surprisingly. We expected to be some sort of bending, but we found little to no bends at all in the wires. And then moving on to traction. During the traction tests, we first added 5 pounds on top of it, and then added a force gauge to it, and we're pulling it to see how much static friction there was on the prototype. And for the first one, we did 3 trials for vertically, or in line with it, and we got the consistent numbers all 3 times, and felt that was good enough data for the force gauge we were using. And then for trial 2, we were pulling perpendicular to like the wheel, and added both 5.5 and 11 pounds on top of it, and got similar data that varied slightly. And then overall, we believe the data fairly accurately depicts how well our design is. However, moving forward, there's currently no CAD model, as I believe we're moving forward with the other wheel.
Yeah, a lot of time. So that was the mesh wheel design.
So, hello. I'm part of the group that made the box grouser wheels, along with John and Anthony there, and I'm Chinook. So we performed 2 tests and on 2 different types of wheels for our prototyping phase. One was with the box grouser wheels, and one was with a wheel with chamfered edges. I'll show a photo of what both looks like now. I just want to get into our prototyping process and our testing process first. So we performed the same tests as the group that did the mesh wheels with only 11-pound load on top of the bottom 30% of our wheels in CAD, which we 3D printed. And then we performed a test for traction and a test for sinkage. Test for traction was when we took that bottom part with the weight on top of it and pulled it with a force gauge parallel to the motion of the wheel. And then for sinkage, we pulled it perpendicular to the motion of the wheel. So these are just what the two designs looked like. So on your left, you'll see the chamfered edge design, which we took inspiration from the University of North Dakota. And on your right, I believe, you'll see the NASA Viper rover box grouser wheel. So for the box grousers, you can see that it's like the rims coming up off the edge above the surface of the wheel. And for the chamfered edge design, you'll see it's like there's like the actual floor of the wheel is extended past the rims and sort of angled downwards as well. So big surprise, the box grousers won. They have way better traction from our results. However, the chamfered edges do have less sinkage, but if you look at the results, it's negligible essentially. The difference between box grousers and the chamfered edges are very negligible. So in the end, we decided to go with the box grousers. There are a few limitations of the test which we did, which is for one, our wheels weren't rotating. We only 3D printed the bottom 30% of it, and we pulled it with a force gauge. So that's a huge limitation. Another one is that we didn't test these two against our current wheels. So there's no really we can't really go based off that. And as well, we only performed trials for one weight, 11 pounds, not like the other group did with 5.5 and 11 pounds. I'll let John get into our CAD design.
Before you do that, so based on those prototyping results between the two groups, we did end up deciding to move forward with the box grouser design over the mesh wheel design. This was mostly due to manufacturing concerns, and there wasn't a convincing difference between the two performances during the prototyping to risk going with a hard manufactured design. However, we are still considering making a full-size wheel since we have a larger budget this year, just to have one and experiment, and it's potentially something we could implement in another year.
Okay, so to kind of go over the basic design here, there's three main parts. There's the rims, the floor, and the grousers. And so the grousers and the floor have these little tabs cut out on the ends of them and then the rims have corresponding tabs that the floor and the grousers interact with. And so the grousers and the floor kind of go in between the two rims, and the two rims squeeze together via the squeeze rods. And so that should interlock the floor and the grousers really nicely without needing any kind of bolt or anything. But some limitations for this design, one is that you can't take out an individual grouser. You could probably kind of jerry rig it together if need be in competition. We don't have a spare for whatever reason. But the bigger limitation is manufacturing this thing, specifically the floor. But kind of going over that, our plan of action for this, first off, the grousers and rim would be 1/8 inch aluminum sheet metal, while the floor would be 16th inch, probably 60-61. Then when it comes to manufacturing the floor itself, because it has to be pretty circular with very little eccentricity in order to fit into the rim, plan on making a giant wooden jig that would be 2 sides of the inner diameter of the floor and then clamp the floor around it, which we would then put the floor into the rims and then clamp it all together. But if that doesn't work, we could also maybe make buy a pre-made aluminum floor and then cut out the tabs on CNC. Or we could, instead of having the floor be like a homogeneous piece of aluminum sheet metal, we could make it into a kind of polygon and then put these individual tabs into the rim. But that's kind of I'm sure there's lots of questions, but we'll get to them later.
Yes, we will be looking for feedback from Bechtel or any members in industry, potential ways to manufacture from a sheet metal to curve it into a large diameter ring, essentially. But thank you, wheel groups. This is our DFMEA. It's pretty consistent with what last year's are.
The main concerns basically boil down to bending in any of our components, but with the amount of FEA we're doing this year, we believe that nothing of failure is likely to happen. I believe the highest probability on there is improbable. So I think we're looking pretty good everywhere else. I don't think there's anything much more to say about that. Our priorities moving forward, our chain tensioner, it looks currently the way it is in CAD, our sprocket might not be large enough to fully tension it to get a full chain length difference. That is something we had discovered last year. We didn't do that analysis, and we paid for it with having to move the gearboxes impromptu, and that was not great. So we're gonna do more analysis on that. Frame weight savings and axis holes, those are in development and very nearly done. It's just completing the FEA analysis, which couldn't have been done until we had full CAD ready. Continue preparing for wheel manufacturing. That's figuring out how exactly we're gonna make that floor. Tolerance in all our dimensions to make sure that things will gonna go together easily and there's not gonna be any tough fits. And then dust covers still have to be done. That's it for drivetrain. I'll now open the floor to questions. Sophia.
We have a question online asking, will the robot be spinning in place again for localization? Will these wheels work well for that?
The question was, will the robot be spinning in place for localization? That software is giving me a thumbs up, so yes. Based on the prototyping results, I would guess that this wheel design would be excellent for that, based on the amount of traction they get, so. Yes, Peter.
On that note, actually, if you go back to the results of the chamfered versus box designs, no, the results.
This?
No, the results. Like the data.
Oh, sorry, I'm having it on two different slides.
Yeah. No, you want it? You get it.
Area.
Perfect. So you said that the difference between them was negligible. I'm seeing that for the sinkage test, the chamfered was almost as much better than the box, as the box was better than the chamfered for inline results. So why is that difference negligible?
I mean, when we look at the average, it's negligible, right? That's when we performed 5 trials.
Wait, what do you mean? What do you mean looking at the average? The average I'm seeing is that for inline traction, the box inline had an average 24 ounces per inches higher, and then for the sinkage test, the chamfered had an average 19 ounces per inches lower. So it seems to me that the chamfered is significantly better in terms of turning or sinkage than the box design, and so I'm wondering why you definitively went with the box, or why it is negligible.
Okay, so that's an error in our slide, but still looking at the sinkage in comparison with the traction, like proportionality wise, the box still gives more of a benefit in traction than the chamfer would give a benefit in sinkage. So that's why we decided to go with the box.
Okay.
The difference of 1, that's an error on this slide.
Yeah.
Can I ask more about the sinkage test? Can you show like the image of it one more time? Because
sure.
The units here are ounces per inch, and I don't exactly understand what.
So the question was just some clarification on the exact test that was done for sinkage. I believe this is the slide.
Yeah, it's that slide.
Okay.
So we weren't trying to get any specific quantitative data. It was more the data as a means of comparison between the 2 different designs. That's why we use ounces per inch instead of some other units. And also on the sinkage thing, the reason that we said it was negligible between the box and the chamfer is because either way, I guess when we looked at the University of North Dakota's design with their wheels, on a video it looked like their bot almost glided over the regolith, like they didn't dig into the regolith at all. And this is something we want to mimic. We thought that maybe it was perhaps the chamfered edge. But when we did this test with that amount of weight, it seemed like both designs just eventually dug into the regolith rather than floating on top. And so it seemed like an inevitable, I guess, byproduct of kind of how this drivetrain is with our wheels turning with tank drive rather than like swerve or whatever, that our wheels are going to inevitably dig into the regolith and shred it. And so we figured that this is gonna happen either way. We may as well have the added traction with the box browsers to kind of help us get over that mound that we created.
Yeah, Max.
Can you go back to one of the first slides with the total ground clearance? Yeah. How is that calculated? Because it looks like the ground clearance is from the bottom of the box tubes to the very tip of the wheel. Do you see that as the ground clearance you have when you're driving with the sink and everything?
These are more just general estimates. I just went straight to the bottom of the wheel as like a best case scenario kind of thing. If we were to be more accurate with eyeballing sinkage, my guess, drop both these numbers down by like maybe an inch, but that's still, at that point, that still puts us at like 1.5 times our clearance from the previous year, give or take. So we're still not concerned, unless we experience severe sinkage issues, which I don't expect to, we should still be, have a decent amount of room.
All right, and then staying with this image here, the sort of the side rim of the entire thing, in the NASA picture, there was a little bit where like the perpendicular browsers, the area in between there kind of narrows down, or the height goes lower a little bit. Have you considered that as a possible weight savings where when it's further from the perpendicular browsers, you kind of cut in, lower that height a little bit?
You're talking about that, the wheel right there. Oh, so the question was, that looking at the sort of the boxes on the NASA's wheel kind of like tapers down for like weight savings, and there's like holes for weight savings. Yeah, that's something we could consider. We haven't considered it just as yet, just for the simplicity of the CAD design and testing it, but yeah, that's something we could consider.
Yes.
I just want to make a comment. For the wheel test, I commend you guys for designing an experiment. It's not an easy problem, so I just want to say that. For the clearance, do you know what the typical size of rocks will be in the competition, or what were last year?
So the question was with the clearance things, the typical size of rocks and just how that will affect things. So if I remember correctly, UCF was piles and then NASA had just big rocks, right? At UCF, those ones weren't a problem, so we kind of just knocked it over. But the main time where we beached ourselves was at our second run at KSC, where I think we were just about caught, I think, if I remember correctly. And we were only floating by like, yeah, the skip plate got caught just barely. So unless they're more like triangle shaped and flatter, we should still be all right. But most of the estimates NASA gives us on like rock size are like diameters for a traversal rather than like going over it in height.
Peter.
Okay, so talking about the chain tensioner.
Yes.
I'll give you a second to pull up the appropriate slide. Perfect. So your current design is just a bolt with a nut on the end. How many? So just one for the logistics. Is the bolt going to go all the way through the frame?
Yes, so the question was for this chain tensioner, is the bolt that holds the sprocket on going to go all the way through the frame? The answer is yes, it will.
Yes. Okay. So does that mean are there going to be 2 or 1 nuts on this bolt?
1.
No, because you could have 1 on the inside and 1 on the far side in order to provide more support, right? But if you have that 1 nut, so the sprocket is going to be running directly on the threads of the screw.
So the question was, will the sprocket be running directly on the threads of the screw? The idea is to get a bolt which is partially threaded so that the sprocket runs on the smooth part, and then the other end beyond the sprocket is threaded for the bolt nut.
Okay, so then the bolt is going. So then you're going to fasten it on the other end. Okay. I'm concerned because we've had problems with tensioning designs like this in the past. We used them on deposition excavation last year, and they were prone to losing, we were prone to, in the course of the vibrations, especially in drivetrain, obviously a very vibration-prone system, prone to loosening and losing tension. That might be mitigated by the use of nylox. Are you considering a more direct tensioning system where the rod would be axially tensioned?
So the question, or rather concern brought up, was whether this system would loosen over time due to vibrations. That is a very serious consideration, which we just haven't had the time to really fully consider. No, we don't have any definitive plans to tension it axially, but if we come across a design or a suggestion that allows us to do that, that is definitely something we would strongly consider implementing. But yeah, it might just have to be that we have to retension this after every run, which isn't a huge deal, but it is a slight inconvenience. Sophia.
So you say the whole entire drivetrain system is going to weigh 17.54 kilograms, and then the frame is going to be 3.89. How much is each wheel weighing or coming in at?
Which was like 1.78 kilograms. It's on the slide.
Yeah. So the question was how much does each wheel weigh? Around 1.76 kilograms per this slide.
And then are you including the motor weight when you were estimating the frame? Or did you just add the motors on to your weight estimates?
I don't believe it's in the frame.
It's in the drivetrain TLA overall. I do believe the motor masses have been overridden in the CAD, I believe.
Okay.
So that should be accurate, that's right now.
Yeah, for clarification, the question was where the motor weights were being accounted for. The frame mass that was on the slide is just the mass of the frame, and then the overall system mass includes the motors.
And like ideally, when you guys are doing cutouts, how much weight do you want to shave off of the frame?
The question was how much weight do we want to shave off the frame? It's really going to depend on how much we can take off without compromising the structural stability of the system. Yes. That's a great question. So the question is, what's the width of the wheels? Outside of the rim, it's 15 inches, I believe. 15 inches. I believe floor to floor, it's 12.75. Yeah, but at most 15 inches.
Have you found a pipe that would be big enough to? That would be a huge pipe.
We got sent multiple pipes from asking around, but none with like the correct thickness.
Okay.
And we also have to like machine it out.
Exactly.
Like a tab. So
I thought that was a very creative idea, but I'm like, that isn't large.
Yeah.
That's like an oil, like.
Another idea which we had, which I don't think we talked, was, let me just go to the next slide, about constructing the floor, which was, if you look at 2, at the right there, is like, take like the best of both worlds from the mesh wheel and our wheel and replace that floor, which John was talking about, with a mesh. It was just an idea that we had that could ease the manufacturability, because we're looking at the photo of NASA's wheel and the way they connected it, it looked like they were just connecting it from grouser to grouser. It didn't look like one whole cylinder of mesh. So that could ease how we attach the floor or mesh, if we decide to do that. That was just one idea.
Yeah.
You don't want to then see something new and try to make that circle. It's going to create stress points in it, and then when you try to weld and fasten it at the top, you've got to imbalance with it. So I go with the second option and hold the mesh to do so. My other concern is you've got 4.5 inch rims of wood. Basically, that wheel's going to start moving more like a steamboat paddle, and that's like one of the rubber wheels. Since your surface area and weight ratio is going to start to set over. So it's going to start to like dig in, like, you know how like steamboat works, right? It's going to start turning the gravel around and actually moving forward. That's why I'm saying we will have to do everything.
Okay. So the concern was with the wheel size and the way the wheels are spaced right now, there are concerns that it would dig into the regolith very quickly. Julian.
With like all the weight saving holes in the frame you're trying to add, is like dust getting into those holes any concern at all?
So the concern or question is regarding the weight saving holes in the frame that will eventually be added. We will plan to put dust covers on there. There are several ideas between just 3D printing for every single one, which is kind of a nightmare. Another popular option is taking a really thin, like 30-second sheet of polycarb or some material like that, and then just covering and lining the entire length of that system such that no dust can get in there and it basically doesn't contribute to the weight at all. Alex.
I'm going to cover things. Are you planning on leaving the sides of the wheels open, or are you planning on covering them up with soft?
That's going to really depend on how they perform when we actually get to that point. Sorry, the question was whether we plan to put covers on the side of the wheels to stop regolith from getting into the sides. We could see how if we put covers on the sides, it would only further worsen the sinkage and turning problem, because it would stop the regolith from allowing to flow through and escape out of there. It's something that we could easily add on in the future that we haven't really considered whether we want it now or not yet. Max.
How confident are you in, do you foresee the welding? Do you have any plans to maybe use that for any parts of either the wheels for like the test or something like that, or maybe reducing fasteners in the frame?
So the question was regarding welding, whether we plan to use that anywhere or could use that anywhere to reduce the need of fasteners. This system was designed with the idea of it being able to easily take apart any component, and welding kind of defeats the purpose of that. There are probably some areas and joints in the frame that could be welded, but when you weld, you lose a lot of that reliability and precision, which with all the other systems that rely on us, that's not something we want to potentially mess with and mess up. For the wheels, we would like it so that they are bolted together so that we can easily remove a rim and replace a grouser or repair anything by a component rather than having to replace the entire wheel. And with it welded, you wouldn't be able to do that.
And for the floor, do you know if you need the entire floor to be a contiguous sheet, or can you have like gaps where instead of having to find a giant tube or bending something like that, you can have sort of smaller sheets in there?
Yeah, so the question was whether that floor had to be one continuous sheet. That is something they had talked about a little bit, where they are considering breaking it up into several different sheets to make it like a polygon or even a mesh between each grouser. That would potentially make it easier to manufacture, especially with the concern that Hotworks brought up with the manufacturing of that floor in the first place. Brian.
Pretty sure I may ask something like that. We used it look at last year for the base group prototype. So probably we haven't done something like that.
Okay.
So, just I'm checking that.
Sure. So yeah, Brian just brings up that it might be possible to bend it. That is something we'll have to look more into. There seems to be conflicting opinions on whether it's possible or not possible. So that is why it is on the top of the list of things to look into post PDR.
The squeeze rods for the wheels, are those custom parts or purchased?
So the question is, squeeze rods for the wheels, are those custom parts or how are those look?
So those we're just thinking those would be like 1032 threaded rod that we just put on the side of with a spacer in the middle. That is at the length of the width of the wheel.
So a 1032 rod that's 4.5 inches long plus?
Yeah.
So are we buying those or making those?
Maybe I think you can just buy like threaded rod online. I think it comes in that length.
All right.
Certainly. Yeah, that's not hard. Any other questions regarding gearboxes, frame, wheels? Peter?
So the grousers, it's my understanding the grousers are not actually, are only attached via the slots on the sides of the rims. Are those going to be clearance fits or interference fits?
So the question is with the grousers, the understanding is that they are only attached by the rims on the side. That is the correct interpretation. The question is, will they be attached with clearance or interference fits? Probably clearance fits would be my interpretation of it.
Okay.
I'm not sure if you have a different answer to interpret.
So do you want them to be able to freely go in and out, or do you want them to stick?
I guess stay. Dude, we were thinking about like chamfering the edges of the tabs so that when we squeeze the rocks together, they almost like wedge themselves into the ring, if that makes sense.
Yes, yeah, so right now the browser is a constant, like height?
Yeah, right now they're constant height.
Okay, I would probably want them to instead have a small step down. So let's have a small step down and then have it be a clearance fit such that it's easier to assemble, right?
Yeah, so Peter's suggestion was just to modify those browsers so that there's a step down and it's a clearance fit into the rim. I think it's a good suggestion for assembly. Alex?
So if the browsers are clear, or if there's anything that's like potentially wrong with browsers, there's a chance the browsers will not be seated perfectly against the floor. Does that affect or damage like performance calculations in any way if the browser can get underneath the browser?
Yeah, so the question is with that clearance fit, there's a potential that there's a little bit of movement in that browser and whether that would affect the performance of these wheels. Probably, but it's probably negligible, would be my interpretation of that. Yeah, Max?
Yeah, in a similar vein with the browsers, have you looked into tabs that sink the browser into the floor, so that there's nothing that, I don't know, if there's something like in the middle of the browser and bends it, it can then come out and, or just stiffing that area?
Yeah, so the question was with those browsers, have we considered attaching them or mounting them to the floor or stabilizing them with the floor in any way?
Yeah, so we were considering adding another tab in the middle of the browser that would bend at a 90-degree angle and then it could pull or rivet through. Maybe not rivet for manufacturing, but yeah. We were thinking about an interface between the browsers and work correctly.
Mike?
I have a question from Haley. She said that there's big cutouts on the side of the wheels. Are you concerned that we're gonna have an X-step problem where a rock gets on the browser and like collides with the box tube?
With the frame and gearboxes? Yeah. Yes, okay, that's a, the question is with the large holes on the side of the wheels, is there a concern that on the inside of the wheels, like here, a rock gets stuck, which would interfere with the gearbox and frame, potentially causing us to stall or damage our system? This, although I wasn't on the team, this reminds me of an issue we had 2 years ago. So there is a 3/4 inch clearance between the wheels and the gearboxes. I think it's unlikely that we encounter a rock that happens to get stuck there and interferes with both the wheels and the gearboxes and doesn't come out if that were to happen. So I think it's very unlikely, but putting a plate on the inside of the wheel, such as like a polycarb to cover that up, would make that impossible.
I'm still pushing to seal both sides, by the way, but you don't have that.
Okay. Julian?
With the wheels being so open, and could dust build up in between like the two hubs of the wheels?
So Julian asked whether dust could build up between the two hubs of the wheels with them being so open. I suppose it can, but these wheels are also constantly rotating. And so I would suppose that it wouldn't build up continuously. They would also drain out from the sides.
It's not what Mike wants to cover though. That's why you're petitioning for.
Yeah. Yes, that is the reason why some individuals want to cover. I will say that there are other individuals who will bring up a concern whether that would make turning significantly harder. So that is something we'll have to look into and test.
Is there a reason why a cover would be like a bad thing?
I believe, I believe, there are individuals who believe that a cover on the sides would prevent regolith from flowing through the wheels.
And then it would cause
It would cause it to be a lot harder to turn.
That makes sense. Okay.
Any other questions? Peter?
With the increased width of the wheel, are you concerned at all about the wheel shafts bending?
So the concern brought up by Peter is whether these wheel shafts would bend with the increased width of the wheels and shaft diameter or shaft length. It's not something we've considered in FEA. These shafts are made out of steel, and my guess would be the failure point would be in the bearings before the shaft actually deforms.
What's the diameter of the shaft?
12 millimeters is the diameter of the shaft. Mike?
Question from earlier as well. How does the output power and torque of the motors compare to the previous, like through gearboxes typically?
So the question was, how does the output of the motor compare to the wheel?
The previous year's.
Okay. So how does the output of the motor compare to previous year's motor?
It's significantly higher.
It is,
Previous year's
yes.
motors were 30 watts, these are 200 watts.
And brushless.
Yeah.
So, okay, so is that torque like 3 times higher than the old one? I don't remember.
That torque is like not even, is irrelevant. I think it's almost an order of magnitude larger.
Yeah, so these motors are significantly more powerful. That is why on there we have it set to achieve the same motor speed as last year. We only have to run 36%, and that's with significantly more torque. I'm not exactly sure what the torque numbers were from previous years though. But to address that, I don't believe stalling will be a concern. I believe if that were to happen, we would have failure points from the keys or elsewhere before that we damage motors. Yeah,
Are those slots on the shaft for keys?
they are. So the question was whether those are slots on the shaft for keys. The reason it is that way is because we plan to buy this shaft directly from Misumi, manufactured. We found that it's approximately the same amount of money to buy a pre-manufactured shaft with the key rings or keyways and the retaining ring grooves. The same amount of money is to buy a full key shaft, at which point we would still have to manufacture a retaining ring in there. So
is the only thing holding the wheel on that retaining ring?
Holding the wheel on is it's not pictured here, but there is a shaft collar on the end for the wheel that will be right here. It's in the other assembly, so it's not pictured in this.
Final question. If you have the shorter key length, are you worried about shearing the keys in the wheels? Because I know in previous years, we thought we were going to break those.
So the question was, with the shorter keyways, are we concerned about breaking the keys in the wheels? I don't believe that's a concern. We have 2 keyways for opposite ends of the wheel, and those keyways are about as long as the previous year's wheels were. So in theory, that's giving us double the keyway length.
Right, machines on right now?
No.
There's anyone in drive?
No. Julian, what's going on?
Next semester.
Question is, does anyone in direction and machine design?
Yeah. If you can find someone who just grab and shake it and do that, just
Okay.
I will say we've done some shear analysis on the motor key, on the key of the motor, and we're fairly certain the motor key is about the same length as those 2. So I'd probably expect that to shear before the other ones, and that happens at I forgot the calculations were, but it was a torque of it was a torque of I think around 60 Newton meters per shear key is what we found.
On the motor one, you're hearing it to lower speed, higher.
Sorry, at the gearbox output is what that is, would shear. So the gearbox output, I feel like probably the gearbox would shear first before the wheels, but maybe I'm wrong, and I'll get either Julian or Josh to check me on that.
All right, so there was just a slight discussion about where keyways might shear. We have done a little bit of keyway analysis for the gearbox motor key, but we will do further analysis to ensure that we're not sharing any keys. Okay. With that, I believe it takes us to the lunch break.
Okay, everyone. So we'll be having a lunch break and the live stream will restart. There'll be a new link for the second half, which will be power and hardware and software. Please be back by 1 from lunch, and yeah. This stream will be back at 1 p.m. Eastern time, so we'll hopefully send out new links, but it'll also be on our YouTube channel.